Alright guys, so in this lecture we're going to be going over how to reduce radicals. And the strategy I'm going to show you is going to help you reduce any radical regardless of the power of the radical. So we'll start here with, for instance, the square root of 9. Now if you know the square root of 9 is 3, well that's awesome. You know, there's no work for you to do. But what if I gave you the square root of 373? For instance, do you know how to solve this? Can you figure out what the number times itself that is going to give you this is? It's not super clear, right? Okay, well what about the square root of 12? What's the square root of 12? What number times itself gives me 12? There's a simpler way to write it, but it's not something that we have memorized like we do with 9. Okay, and so not only does this strategy help for square roots, this is also going to help for instance, like we had 32. What's the fifth root of 32? This strategy is going to work for no matter what the power of the radical is and no matter what the number on the inside is. So even if we had 32x to the 6th, y to the 700th power, the fifth root of all that, this strategy will help you figure out how to reduce the radical into its simplest form. So we're actually just going to work on this one, and I'm going to go slow and write as neatly as I can. And if you still have questions, like, let me know, because this is something that a lot of people stumble with in algebra. So (32) x to the 6th, y to the 700th power. Cool. Well, notice how in all of these it's just something, like one thing by itself to a power, and x to a power, y to a power, x to a power, but this is not to a power. So we need to fix that. We need to write all of our numbers so that they look like something by itself to a power. And how do we do that? Well, we use a prime factorization tree. So we're going to take 32 and we're going to prime factorize it all the way down to its prime factors. Remember, numbers like 2, 3, 5 are prime because the only numbers that divide them evenly are 1 in itself. But 9, that's not the case, right? Because 3 divides 9. So 9, 16, 4, these numbers are called composites. Composite numbers. And these are prime. And these two things are mutually exclusive. So if you're in one, you're not in the other. If you're a prime number, you're not composite. If you're a composite, you're not prime. So let's factor this into primes. So what number times another number gives me 32? We just need to factor it. And so, well, you're like, okay, 32 is even, so I know 2 does. 2 times what? Okay, 2 times 16 is 2 prime. Yeah, so I can circle it, and I don't have to worry about this side of the tree anymore. Let's break down 16, and you're like, okay, 16 is 4 times 4. Cool. Okay, well, is 4 prime? No, it's 2 times 2. Okay, same for this 4, 2 times 2. And now, since we all have 2's everywhere, these are all prime. Okay? And so what we're going to do is we're going to rewrite 32 as 2 to the 1, 2, 3, 4, 5 of them multiplicatively, right? Because they're all being multiplied to make 32. So we can replace that with 2 to the 5th power, because that's what 32 is. And so notice here, though, this isn't a square root. When it's a square root, we have an invisible 2 out here, right? But this is a 5th root. Okay? So how are we going to attack this problem? Well, now that we've got everything into this form where it's 2 to a power, or excuse me, 1 thing to a power times 1 thing to a power times 1 thing to a power, we can use this strategy. So when we have variables to a power, they're the easy ones. It's actually the numbers that make this more difficult. But once you've prime factorized it and you've got it to this form, now they're all a lot easier to deal with. And so what we do is, what is the number that has, what's the base of the exponent? The base of the exponent is 2. So we're going to write 2, and we're going to put a square on it so we don't forget what number we're working with. Okay. What's the power of the radical? 5. And then you put the power of the 2 inside of the division symbol. we're going to do long division essentially. Okay, so that's our first one. We're going to do this for 2. Let's look at our next variable. Okay, so now we have x, right? So what we're going to do is we're going to put x, and then we're going to put a square around it so we don't forget what number we're talking about. Notice that the radical here is the same for all of these, so it's always going to be 5 into something, regardless of which one we're talking about. So for y, we can kind of jump ahead to y, put a square around it so we know what the letter or number that we're talking about is. It's going to be 5 into something, and the number that the 5 divides is the power of that particular variable or number. So in this case, the power of x is 6, so 6 goes in here. The power of y is 700, so 700 goes in here. And so all we need to do now is division. So we'll start with the 2 first. How many times does 5 go into 5? It goes into it once, right? 5 times 5 is 5. Subtract and you get 0. So does 5 go into 0? No. So all you have to do is write remainder 0. Cool. Let's work on this one. How many times does 5 go into 6? 1 time. 5 times 5 is 5. 6 minus 5 is 1. Does 5 go into 1? No. So our remainder is 1. Cool. Same thing here. How many times does 5 go into 7? It goes into it 1 time, right? 5 times 1 is 5. Subtract, we get 2. 5 doesn't go into 2, but look, we have other numbers to bring down. So let's bring this 0 down. Does 5 go into 20 evenly? Yes, it does. 4, right? So now we have 5 times 4, which is 20. And we have the 0, but we still have another 0 to break down. So, and how many times does 5 go into 0? Remember, this 0 isn't what's left over. It's being brought down, so then we need to put another 0 here. Okay, so 5 goes into 700 140 times, and once we do this final 0, our remainder is going to be 0. Cool. So now how do we evaluate this original expression we started with? So we started with this. We wrote it as, after we did the prime factorization, and now using this, these values here tell us how many of each number or variable get on the outside of the radical and how many have to stay in. The first number tells you how many are on the outside. So we have 1 remainder 0. That means 1, 2 is on the outside. And none of them are left on the inside, so we're not even going to write anything. Okay? How many x's are on the outside? 1 is. So we put 1 x on the outside. How many x's on the inside? So now that we have something greater than 0, we're going to put 1 x on the inside. Okay? How many y's are on the outside? Well, 140. So we just write 140 as the power. And how many y's are on the inside? None, so we don't have to write anything. So if we were to simplify this, 2 to the first power is just 2. X to the first power is just x. We have y to the 140, and then root x, because x to the first power is just x. And so this is our simplified answer, and we're done. Now, why did I say like don't write anything when you have remainder 0, or if you have a 0 anywhere? Where you could technically write something for like the 2, right? We had 2 which had 1 remainder 0, so you would say 1, 2 on the outside, 0, 2's on the inside, but multiplicatively. And so if that was the case, 2 to the 0, any number to the 0 is just 1, right? So this is equal to 2 to the first times the square root of 1, but the square root of 1 is 1, right? So this is just going to give us 2 times 1, which is just 2. So that's why there's really no point in writing the 0 here, right? Because it's basically 1 and the square root of 1 will go away. Even if it was on the outside, if it was something like this, right, there would be no point in writing this 2 because this is just an actual 1 times the root of 2, which is just going to give us root 2. So anywhere you have a 0, if you're multiplying by 1, you're not changing anything, so you don't need it. Okay? So this is a confusing topic for a lot of people. You may not like this strategy, but this strategy works for every radical, regardless of the power of the radical and regardless of the number on the inside. If you have any questions, please don't hesitate to ask. I just wanted to keep this one short. I'll see you in the next one.